Hi everyone, so now this is the lectures for our week 4, okay, lecture week 4, and we are going to talk about the energy expended in moving a point charge in an electric field, right? So this is our lecture, week number 4, so it's energy expended. Expended in moving a point charge in an electric field. Alright, so let's look at these situations. So if you have a positive charge here, right, and you have a negative charge here, okay, so you know that the electric field surround the positive charge will terminate at a negative charge. Am I right? Okay, so this is what you know, okay, because the electric field for the positive will be outward, and for the negative charge it will be inwards. Now imagine I put a positive charge here, right? So this positive charge will actually experience a force because of this positive charge, okay? This positive charge will repel it, okay, because they have the same polarity, and this one will actually attract it. Okay, so if I want to move this positive charge from point A to point B, okay, meaning that I'm moving in the opposite directions, I have to apply external force. Am I right? So I have to apply the external force. So in order to make this positive charge to be stagnant, okay, to be static at the positions, okay, the F, okay, that is due to the charge, okay, will be equals to the negative of the F external. Okay, so this is the condition that because when we add the F together with the X externals, it will be equal to 0. When it is equal to 0, that means that the charge, the red color charge will be static, okay, maintained at the positions. So F, we can calculate it by using our formula earlier, which is equals to the QE, and it is written as F external. So our F externals will be equals to negative of QE. Okay, so if we want to know what is the work done, okay, to move the charge, okay, so we have to apply this formula. Work done is equals to integrate the F external, okay, dot dl, dot dl. Okay, so if we replace the F external with the QE, okay, then it will be like this. Okay, you will have a negative. So the work done will be integrate from A to B. Integrate, okay, we move the charge from point A to point B. Okay, so this is the work done by the external force in order to maintain the position of the red charge, okay, at the same positions. Right, so if you look at this, the position, maybe I will give it a direction first. Over here is the X directions, and over here is the Y directions. So at these portions, our electric field will be in the negative Y directions. Right, this is positive Y. So this direction will be negative Y. So if we put the directions into it, and the length is depend on the axis y. Okay, this one is depend on the axis y, moving in the y directions. Okay, you see that this is negative. You will see that you will get your answer equals to positive. So meaning that when your work done is positive, okay, so the external force is playing the role. Okay, so the external agent that perform the work. So external force perform the work. Okay. If now the Q is a negative charge, okay, Q is a negative charge, meaning that if you want to move this negative charge, okay, from point A to point B, in fact, you don't need to apply external force. By right, the force we already push this charge, okay, towards the directions upward. Okay, so in this case, you will see that your work done will be negative. Okay, right, it will be negative because it is a negative charge. So when it is negative, the work done is negative. Okay, it means that the force, okay, the work done is by the field, okay, by the force. The work done by the F, by the field, by the force. Now we are going to relate this work done, okay, with the term that is called potential difference. Okay, potential difference. Okay, potential difference V, or to be more commonly, you will say that is the voltage difference. Okay, voltage difference. Okay, voltage difference. So this potential difference, the V is equals to the W, the work done, okay, divide with the Q. Okay, so this also means that you have a work done just now, A and B, right? You have a negative. This one I put a general formula. You have a Q, right? Okay, this we get it from here. Okay, we get it from here. We divide it with the Q. Okay, so you can cancel the Q, and the voltage difference or the potential difference between these 2 points A and B is equals to integrate from A to B the electric field along the length. Okay, so this one we will write it as the VAB. That is the potential B minus the potential A. Okay, so now let's imagine if the electric field over here, okay, is from a point charge. Point charge is from a point charge. So for point charge, right, the equation for the E will be this one. And now we are going to put this thing into the integral part over here. Okay, So it would be negative integrate A to B. Then you put your Q over 4 pi epsilon naught R square R. And for the dl over here, okay, it is a vectors. Okay, so you have to put the dl, or you have to pick the dl of spherical coordinate system, because this one is actually the spherical coordinate systems. Okay, so you can refer to your formula. Okay, the formula, we look at the dl. Okay, so this is a dl for spherical coordinate systems, so you have to use this one. Okay, so it will be equals to, okay, just putting this one here, dr, r directions, okay, r d theta, theta directions, and r sine theta, d phi, and phi directions. Okay, so the whole thing over here actually represent the dl, the dl, okay, for spherical coordinate system. Spherical coordinate system, so don't confuse. Now you dot product it. So when you perform a dot product, means that you have to look at this thing, dot product with this one dot product with this one, and this one dot product again with this one. Okay, so when you dot product, I think I explained before, you can refer here. Okay, what happens if you dot product with directions, okay, that is difference and same directions, you will get 1 and you will get 0. So over here, the term for the theta and the phi will be missing. Okay, so just left these R components, so you get this A and B, Q over 4 pi epsilon naught R square dr, okay, R square dr. So you focus on the integrations for the R. You can take out the others. Okay, take out this thing, negative Q 4 pi epsilon naught R. Oh no, R you have to put it inside, yeah. Okay, so then you integrate A and B, and you put R negative 1 dr. Okay, so you will get negative Q 4 pi epsilon naught. So you will get 1 over R. Okay, this is negative 2. Okay, integrate you get R negative 1. Okay, R negative 1, and then divide 1. Is it okay? Divide negative 1. Okay, so this negative 1 will be here. Okay, so you can cancel out both negative here, and then replace the value. One over RB minus 1 over RA. So the VAB, okay, will be equals to these equations. Right, these equations. Okay, the VAB. This is the formula. Okay, so this is the VAB. Right. Okay, so I will explain to you how to use these formulas. So this is the example 17 in the PowerPoint slide. So now you have a point charge, and Q1 equals to negative 4 nanocoulombs, and located at the positions 0, 0, 0. Find the electric potential, okay, that is the V, okay, when the Q2, when the charge is moved to 042 from infinity. It is assumed that the V infinity is equals to 0. Okay, so what would be the formulas, okay, for the electric potential? Okay, so we refer to this formula. Okay, we'll be using this one. So the VAB is equals to Q over 4 pi epsilon naught, right? And then you have the RB and you have the RA. Okay, so this VAB is equals to VB minus VA. So now this charge is moved to this point from infinity. So this is the point A, this is the point B. Okay, so question telling you that the voltage from the infinity is 0, meaning that the VA is equals to 0. So you can cancel this part. Okay, you can cancel this part and focus on the VB. Okay, so here come to the question on what is the Q. Okay, so the Q is the source of electric field. So the source of the electric field is actually contributed by this Q1 that is located at 0, 0, 0. Okay, 0, 0, 0. And then this RB would be the distance between the coordinate of Q1 and also coordinate B. The B, yeah. Okay, so this one is the distance, the distance. Okay, so the RB will be equals to the magnitude, the magnitude of taking this 042 minus the 0, 0, 0. This one is the distance. So you see, I put the magnitude. So you will have a 042. Okay, and your magnitude is square root 20. Okay, so the potential would be -4 nano. Okay, divide 4 pi epsilon naught and then multiply 1 over square root 20. Okay, so this one will be the potential at the point B. Okay, 042. Okay, so this one you can cancel it. So you have a negative negative 8.04 volt. And this is the VAB. Okay, negative 8.04. Okay, now we look at the next example, example 18. Okay, also in your module, in your PowerPoint slide. Okay, you have 2 point charge. Okay, so these are the value of your point charge, and they are located at the following equations, and you have to find the potential at these positions. Okay, find the potential at 1, 1, find the potential at 1, 0, 1. Assume the V is 0 at the infinity. So in this case, you see you have 2 charges. So 2 charges will contribute to 2E. Okay, so the equations for the voltage, okay, will be equals to this one, Q over 4 pi epsilon and 1 over RB minus 1 over RC. So this one is contributed by only 1 charge. Okay, so if you have a second charge, okay, so this one will be Q2. Okay, so Q2 epsilon, then 1 over RB minus 1 over RA. This one should be RA. you follow the formula. Yeah. Okay, so the voltage or the potential difference at the V101 will be the summations of a V1 and V2. Okay, let's do it slowly, yeah. So for the V1, we know that it is from the Q1. Q1 is a negative 4 micro over 4 pi epsilon naught. So the RB over here would be equals to the distance between the observation point, okay, the point that you want to find the potential, and also the locations of your Q1. Okay, location of your Q1. So for the RA over here, okay, it will be equals to 0 because it is already stated here at infinity it will be 0. So these two, they will be 0. Okay, they will be 0. So we just focus on looking the RB. Okay, so the RB you can find it by putting the value. Okay, so the RB will be the magnitude. The magnitude of taking the 1, 0, 1. Okay, so this is the point that you want to know the potential. Okay, minus the 2, negative 1, 3. 2, negative 1, 3. Okay. So this one you will get your answer equals to negative micro pi epsilon naught. So you will have 1 over okay, so this one will be a value. So you will have this pi epsilon naught, and you get the magnitude be square root 6. Okay, square root 6. This is the V1, V1. Negative so this one would be negative 14.68 kilovolt. Kilovolt. Right? Okay, so this is the V1. Okay, V1. Then we look for the V2. Okay, so V2 will be the same thing. Okay, but now you focus on the coordinate of Q2. So 4 pi epsilon naught 1 over RB. Okay, so now the RB is the distance between the point that you want to find the potential and the locations of the Q2. So Q2 in this case is equals to 5 mu. Okay, 4 pi epsilon naught, and the distance will be, observation point is 1, 0, 1 minus 0, 4, negative 2. 0, 4, negative 2. 0, 4, negative 2. So you will have 1 over 1, negative 4, 3. Okay, so this is the magnitude. Okay, so you have 5. So you can look for the answer. Is the square root 26. So it is 8.81 kilovolt. Okay, 8.81 kilovolt. So now you combine them together. One is negative, the other is positive. So the V total will be minus, okay, negative 5.87 K. Okay, so this is the potential difference at the position 101. Okay, when you have two charges, two sources of electric field. Okay. Alright, we look at the next questions. So now you have a point charge. 5 nanocoulomb is located at the origin. If the voltage is equals to 2 at this position 0, 6, negative 8, find the potential at A and B, then find VAB. Okay, so find VAB. So the first information is we know that the potential is equals to 2. Okay, is equals to 2 at this coordinate. Okay, so if you try to relate with the formulas that we have, the formulas we have is we must have a Q, right? For the potential, the equation of the potential is we must have a Q, then this one is the B, right, minus the RA. So in our previous case, okay, this RA, we just assume it to be 0 because the question said that it is 0. But in this question, they didn't tell us what is the VA. They didn't tell us what is the V infinity in this case. Okay, so we cannot say that it is 0 because it didn't mention. The only thing that we know is it is equals to 2. Okay, it is equals to 2 at this position 0, negative 0, 6, and negative 8. Okay, so we have to find the VA over here. Okay, we have to find the VA over here. Okay, so we look at we try to fill in the blank. Okay, so Q is, we know, we fill it. Okay, and then 4 pi epsilon naught, and RB would be the distance, right, between the observation point, okay, that is the 0, 6, negative 8, minus, okay, the locations of the charge, which is 0, 0, and 0. Okay, and then minus 1 over RA. RA, we have no idea, right? Okay, but we know that it is actually representing the VA. VA. Or the V infinity. You don't confuse the VA over here with the VAB over here. Okay? Don't confuse that. They are not the same, okay? Just a labeling. Okay? They are not the same. Okay? So now we try to calculate. So this one will have 36 plus 64. So we have 10 minus 1 over RA equals to 2. Okay, so if you multiply it inside, okay, so this one will be this one will be 4.49. I multiply this one inside. Okay, so this one will be the VA, no, VB, minus the VA. And this one is the VA. Okay, is equals to 2. Okay, so from this relationship, we can find the VA. We don't want to find the RA, we want to find the VA. Find the VA. So we're taking the 4.49 minus 2. Okay, so our VA is equals to 2.49. Okay, our VA is 2.49. So means that, okay, the voltage that we are comparing over here is not equal to 0, but 2.49. Now we look at the second case. Okay, this is the other case. This one. Okay, find the potential at A. Okay, this is another case already. So to find the potential at the position A, okay, we go to the same equation again. Okay, so this part, okay, we have idea already what is the value, okay, from here, right? Okay, so if we expand it, this one will be 4 pi epsilon naught RB, okay, minus Q over 4 pi epsilon naught RA. Okay, so the Q over here is this charge, the source of the electric field. Okay, so this one we already calculate just now, and it is equals to this, 2.49. 2.49. So we will put 2.49 over here, and 5 nano. Okay, we're putting the 5 nano over 4 pi epsilon naught RB. Okay, so RB we have no idea, so we have to find what is RB. So RB is the distance between the observation point and the source point. Okay, observation point is -3, 2, 6, and the source point is the origin. Okay, the source, the source that contribute to the electric field. So it's the -3, to 6 divide at minus 0, 0, 0. So we have 9 plus 4 plus 36. So 49. Okay, square root 49 is equals to 7. Okay, so you now can replace the RB with 7. Okay, RB you can replace it with 7. Okay, so this one will be your VA. Okay, VA. So it's the 5. So it's equals to 3.93 volt. Okay, this is the VA. Okay, VA means the potential at positions A. Okay, now we move on to find the positions at to find the potential at position B. Okay, using the same formula, same technique. So this is the VB. Okay, we still have the same charge. Okay, 5 nano. Right, we still start from these equations. Right, so we have a 5 nano over 4 pi epsilon naught RB. Okay, and then minus 5 nano over 4 pi epsilon naught RA. Okay, so for the second term, we already know what's the value, right? It's 2.49. Okay, so we just replace it with 2.49 later on. So now we need to know what is our RB. So our RB will be the point that you want to look for the potential, that is the 1, 5, 7, minus the coordinate of the point charge. Okay, so you will have your RB equals to 1 plus 25 plus 49 square root 75. Okay, so you replace the RB here with square root 75. Okay, now calculate 5 okay, and then you minus 2.49. You get 2, this is your VB, 0.769698, something like that. Okay, volt. Okay, this is your VB. Now, what else? Then find the VAB. Okay, find the VAB. So what is VAB? VAB means you take the VB minus the VA. Okay, so the VB you have calculated it to be 2.698 and you minus your VA, which is 3.93. Then you get negative 1.23, something like that. Okay. So this one is the potential difference, VAB. Okay, so I hope at the end you have idea how to actually apply these equations. Okay, when we say that we are finding the potential, okay, the potential, we are actually comparing the potential between two positions. That is the position B and also the position A. So under normal conditions, usually we will compare it with the potential at infinity. Okay, potential at infinity, and it is usually we'll put it as a 0. Okay, but sometimes like in this equation it is not equals to 0, so you have to find it out. Okay, and this one will represent the source of your electric field. You have electric field because you have charge. Okay, so this is the source of the electric field, and the RB, okay, would be the distance between the charge and also the point that you want to find the potentials. Okay, you have to, this one is the place that you want to find the potentials, and this is the locations of your charge. Okay, so this is how you define the things to find the potential at one point. Okay, so if you have get the potentials at 2 points, they are asking you to find the potential difference across these 2 points. You just minus terms, okay, you can get the answer. Okay, so this is about the potential difference.